Hello, students of physics. We're looking at sound still. And what I want to do, we've already looked at this page. This is the page where we talked about a vibration causes a sound, and we went in and we looked at the human vocal cords. You did this as the indoor activity just the other day, where you were going through and looking at all kinds of things related to sound on that document. And after we did that, we talked a little bit about the speed of sound and what the speed of sound is and how you can use lightning and sound to figure out how far away a storm is. And then finally, we looked at adjusting the speed of the sound using a couple of math formulas. So we could take the speed of sound if it's not at 0 degrees centigrade, and we could actually figure out how fast that is. So what we're going to do today is to go a little bit further into that packet that you did, that 26-1 packet, and we're going to look at some properties of sound. So here is that 26-1 packet that you were filling out, and we're going to look a little bit at intensity today, pitch, and tone. So I'm actually going to start with pitch, but you kind of already have notes on it. That was the purpose of the handout. If you did it online, then those notes are going to be in your Google Drive. But if you were able to print it, then you have those next to you, and that's great. But if not, you can always pause this video at any point in time and write some of this down so that you have it in a note form. That way when you're taking a test or a quiz, you have it available to you. So pitch is, got to get down a little bit, the high and low frequencies that we are able to hear. And when we say frequency, what we're referring to is like a high note or a low note. And that's what pitch is. If it's a high frequency, that tends to be a high pitch. If it's a low frequency, that tends to be a low pitch. So for example, there's a lot of different ways that I can demonstrate this to you, but I got one right here. This is just a little kid xylophone that I found on my computer. And notice how long the metal bar is. If it's a long thing that I'm going to vibrate, that means it's going to make a long wavelength. A long wavelength means low note. Long wavelength, low note. Short wavelength, high note. And you can actually almost like you could measure these, and if you were to measure these, this is the thing that's going to vibrate, so that's the size of the wave. So from here to here would be one wavelength in this particular thing. So large wavelength, long wavelength, low note. Short wavelength, high note. I happen to have another item here, and it says demonstrate with the oscilloscope. So if I wanted to demonstrate this to you with the oscilloscope, first thing I'm going to do is go big with my webcam, howdy, and this is an oscilloscope. This is a wave generator, and I put a speaker on top of it. I'm going to position my camera so that you can see the wave generator and the oscilloscope at the same time. And there we go. That looks pretty good. So the wave generator is on, and what it says right now is that it is a frequency of 392. And let's put it so that we can see the wave on the screen. There we go. The wave on the screen looks like that. So hopefully you can see that wave nice. And if I turn, if I change the frequency, if the frequency is lower, the wavelength is going to get longer. And you could see that. And if I change the frequency, if the frequency gets higher, the wavelength gets shorter. And you can see that as well. I also have my guitar here. My one-man guitar. I showed you that the other day. My one-string guitar, I meant to say. And if I just leave it from here all the way up to there, that's one long wavelength. But if I push on it somewhere, like that, and play a note. I made the wavelength shorter so the note's higher. And if I move my finger up here, I made the wavelength shorter so the note's higher. So high frequency is a high pitch, which is a short wavelength. Low frequency, low pitch, long wavelength. Nothing shows us this better than the good old Blue Man Group video. See, by doing this, he made the wavelength longer, which makes the note lower. Shorter wavelength, higher note. If you've never had a chance to see Blue Man Group, I'd highly recommend it. I just jumped ahead a little bit in the video to speed up the process. They've gone to new locations now. And then this is just this part of the show. I mean, it's what they do. If you've never seen Blue Man Group, it's definitely worth checking out at some point in time. But there you go. I think we got pitch and frequency and wavelength and how they're related, tied together pretty well. What is the range of human hearing? Well, the range of human hearing, the lowest we can hear, is supposed to be 20 hertz. And the highest that we can hear is supposed to be 20,000 hertz. So I'm going to show you those with the oscilloscope if I can, just to see. I'm not sure how well this is going to come through on the camera, but we're going to try it. I'm going to turn my oscilloscope on, and I'm going to put it over there. I'm going to pause the video for just a second so that I can get down to 20 hertz for you. I do have the volume all the way up, and you can see this is the lowest, or the loudest that the volume will play, just for the record. And I'm at 186 hertz, so there's 186 waves per second. And when I drop down, I'm not sure we can hear anything, but you can see on the screen how long the wavelength is. The lower the note, the longer the wavelength. I could try to get all the way up by 20,000 hertz. And I'm going to have a similar problem when I do that, but I'm going to pause the video. Right now I'm at 544 hertz, or a frequency of 544. So just for the record, this is 4,240. And as I increase, you can see how short the wavelength is over here. As I increase the frequency, this is 7,000 hertz. 7,320 to be exact. 9,000 hertz. And if we get up into this range, most humans at this point, and I have no idea if the microphone on this camera can pick this up, I can barely hear it. You can see the waves on the screen. That's 13,000 waves per second. 13,000 waves per second is what we're looking at. And if now that's 26,000 waves per second. We can't even see them on the screen anymore. They're so close together. But there's no human alive that can hear that frequency. I'm going to shut that off and get back to, like I said, there's no human alive that can hear that frequency. There are other animals that can. So, for example, if we go down a little bit, a dog has a much greater range of hearing than we can. Dogs can hear all the way up to 25,000 hertz. Right, Nala? Yeah, you can hear 25,000 hertz, can't you? You could probably hear that. It was probably driving my dog nuts when I just had that on the oscilloscope a minute ago, up around 25,000, probably driving her crazy. Cats can hear even higher than that. This is why we have dog whistles. Sometimes people play a dog whistle and like, it's not making any sound. It is making a sound. It's just that the sound is too high for us to hear with our ears. Our ears have a very limited range. We can only hear 20 hertz to 20,000. Anything below 20, can't hear it. Anything below 20, that's what we call infrasonic. So that's kind of a vocabulary term. Might want to write that down. Infrasonic is anything below 20 hertz. Ultrasonic is anything above 20,000 hertz. So we define those. Ultra means above. So above 20,000. So dogs and cats have ultrasonic hearing. A dolphin, by the way, a dolphin can get all the way up to 150,000 hertz. So I found this on the internet. This is all different animals and what their range of hearing is. It's something that you can easily look up. I'm not going to put something like this on the test, but I might ask you, like, say, what a dog could hear or what a cat could hear. So those are definitely worth writing down, things that were in the notes. But it's just kind of interesting to look at the list just to see, how your range of hearing compares to other living things. One of the things that I would say that is interesting is even though most animals have a much wider range of hearing than what we have, for example, the raccoon can hear from 100 to 40,000 hertz. That's a wider range. They can't distinguish as many frequencies as we can. So that means, like, if you're playing a note at 392 hertz, and then you change it to 390, we can hear that. I could even do that as an example right now. Here's 284 hertz. If I change it a little bit, you can hear that difference. And other animals would never be able to distinguish between those two sounds. So even though our range is narrower, we're more fine-tuned. Within that range, we have the ability to distinguish the sounds better than what other animals do. Another part of your packet that was really nice was there's a part about it on the human ear and how we actually hear those sounds that we hear. So in my notebooks, I have this slide which kind of demonstrates how the ear hears. I'm not going to read the words down here, but sounds come in the sound waves. Remember, it's a longitudinal wave or a compressional wave. And they come in and they make the eardrum vibrate. And then once they make the eardrum vibrate, there's these three little bones, the hammer, the stirrup, and the anvil. It's actually hammer, anvil, stirrup. And those three bones will then vibrate as a result of the membrane vibrating, which then sends impulses into the liquid-filled part of your ear, which is the cochlea. And when that liquid moves, it makes the little hairs inside of the ear move. And then those little hairs send the sound wave to our brain. And it's like, I think the whole process is actually amazing. Your packet really does do kind of a nice job of explaining how that works. But the notes are also good here. So if you don't have any of that written down, it'd be worth having on a piece of paper just because of we're going to take a test on this, last test of the year. And you might want to have those things written down so that you have those available to you. The Doppler effect is an amazing part of this whole frequency. Every little kid that's ever had a toy car knows the Doppler effect. You give a little kid a toy car and you say, go play with this toy car. They're going to put it on the carpet and they're going to go like, meow. That's the Doppler effect. Believe it or not, the car doesn't actually make that sound that changes its pitch like that. The frequency doesn't change. An engine in a car is always the same. It's like an auditory illusion. You've heard of optical illusions. Those are illusions that affect your eyes. There's audio illusions as well. I'm going to go back to this ear because optical illusions play tricks on your eyes. Audio illusions play tricks on your ears. So here is an audio illusion.
Have become quick to catch illusions that trick our eyes, but how often do you consider illusions of the ear? Are you really able to trust your ears and the things they hear? For example, listen to Greg speaking.
Bar, 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 bar.
What do you hear? If you heard bar, 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 you'd be right. But how about now?
Bar, 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 bar.
Chances are you heard far, far, far this time with an F, except you didn't. In fact, the audio didn't even change between the two videos.
Bar, bar, bar.
Strange as it may seem, what you hear depends on which video you're looking at. Go ahead, take turns watching each video and see how the sound morphs.
Bar, bar, bar.
This is a perfect example of something called the McGurk effect, which shows how our visuals can alter what we believe we're hearing. Now I want you to count how many times you see a head. Take turns watching each video and see how the sound morphs.
So basically what they're saying is if you watch this video, you're going to hear bar, bar, bar. And if you watch this video, you're going to hear far, 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 even though the audio is exactly the same.
Morphs.
Bar, bar, bar.
This is a perfect example of something called the McGurk effect, which shows how our visuals can alter what we believe we're hearing. The video you're looking at. Go ahead, take turns watching each video and see how the sound morphs.
Bar, bar, bar.
This is a perfect example of something called the McGurk effect, which shows how our visuals can alter what we believe we're hearing. Now I want you to count how many times you see a circle flash on screen. Let's do that one more time. Did you see it flash twice? Many people do, yet without the sound, it becomes clear that the circle is only flashing once. In this case, the sound has altered your perceived vision. The next one works best with other people around. I'll play two tones, and you tell me if they're ascending or descending. In other words, are the notes played from low to high or high to low?
So since he said this is better to do with people around, I got the help of Amanda and Sam to help me. We're going to see if we hear them go from low to high or high to low.
Oh, listen to this.
Low to high. Yeah, what she said.
I said high to low.
No, low to high.
High to low. No, I'm not doing it again. Listen. Shh.
Which was it? How about this one?
High
to low. High to low.
High to low.
High to low?
Yeah.
Okay. You guys may or may not disagree or agree with us.
Write down what you heard for each number and let us know in the comments. Chances are, if you compare with enough people, you'll all have different answers. Surprising? Try some more.
Low high.
Low high.
And this one.
High to
Low
low.
high.
High low. Do. High to low.
How is it possible that you're hearing something different from others? It's an auditory illusion called the tritone paradox. It's created in such a way that the tones contain both a higher and lower frequency in them, but our brains have a preference of which to listen to. Diana Deutsch, the creator of this illusion, found that your geography and language from infancy all play a role in deciding this preference. Finally, listen to this audio clip of a gradually climbing tune.
I love this one.
And yet, if I play the exact same clip back to you, it will sound like it's only continuing to climb higher and higher. I swear this is the exact same clip I just played. You can rewind that section of this video over and over and check for yourself. Try it. Each time you start it over, the tune is seemingly climbing even higher. It's called...
I'm clicking the back button. Oh, yeah, let me get down.
And yet, if I
Mine didn't start over that time. The first time it started over, but that time it didn't.
And yet,
That time it started over.
That's crazy.
Our brains are superior.
Alright, that's
and
it.
yet, if I play the exact same clip back to you, it will sound like it's only continuing to climb higher and higher. I swear this is the exact same clip I just played. You can rewind that section of this video over and over and check for yourself. Try it. Each time you start it over, the tune is seemingly climbing even higher. It's called the Shepard tone illusion, of which there are many variations.
The LEDs that
So back to the Doppler effect. The Doppler effect is an audio illusion. What happens in the Doppler effect is sometimes we think of the sound waves as being like these concentric circles. I have this great applet that I found on the internet that kind of shows that. Here's an airplane, and if the airplane were just sitting there with its engines on, the sound waves would move out in all directions, and they'd be equally spaced apart. So the distance between here and here would always be the same. But watch what happens when I put the airplane in motion. When I put the airplane in motion, the sound waves are still moving out equally in all directions, but because the airplane is moving in the same direction as the sound waves, these look like they're really squished together, and these look like they're really far apart. So somebody on this side of the airplane would hear a higher pitch, because the wavelength is shorter, and somebody on this side of the plane would hear a lower pitch, because the wavelengths are longer. Let me make the plane go a little bit faster this time. And you'll see the effect even greater because the plane's traveling faster. Look at how squished together the waves are. This would be a really high pitch for the engine of the plane, and this would be a very low pitch. Now we can actually make the airplane fly faster than the speed of sound. They can do that, and when they do that, it's said to break the sound barrier. And not quite there. Let me get just a little bit faster. There we go. So the airplane at this point is traveling faster than the sound it's making. And if the airplane's traveling faster than the sound, this is actually called a cone wave. And I think you can see it. It's kind of three-dimensional. It's pretty cool. It's one of the terms, one of the vocabulary terms for this unit. It's going to be coming up in just one moment. Let's make it go even faster than the speed of sound by quite a bit. This airplane is flying faster than the speed, and you can definitely see why it's called a cone wave at this point. But like I said, that come up in just one moment. So I'm going to close this app and get back over to the notes. So here's my example that I put into my own notes. If the source or the observer are not moving, this is what sound waves would look like. They would go out equally in all directions. If either the source or the person is moving, we get this illusion. The sound waves are still being produced at equal intervals, but we get this illusion that one side's squished and the other side's spread out. On the squish side, it's a higher pitch because the wavelength is shorter. And on the tail end, it's a lower pitch because the wavelength's further apart.
The phenomenon called the Doppler effect changes the pitch of sound waves when the source of the sound is moving relative to the listener. As the train approaches, sound waves from the whistle are crowded together in front of the approaching train. The crowded sound waves produce the relatively high pitch heard by the listener on the platform. As the train moves away, the waves are spread out, producing the relatively low pitch heard by the listener.
So there's a really super quick example of it. So like I said, we have a couple of vocabulary words that we can relate to this. If you're talking about whatever the source of the wave, if the waves are stacking up in two dimensionals, so like if the source is moving faster than the wave, and the wave is only made in two dimensions, that's what we call a bow wave. And a great example of that would be like a ship. See, there's only two dimensions that this wave is moving into, and this is what a bow wave would look like if the source is faster than the wave, but it's three-dimensional. This is called a cone wave, also known as a shock wave. And a shock wave is, when something breaks, goes faster than the sound wave. So here's an example of it in real life. I mean, I showed you that jet plane I showed you the jet plane app that I had. This is like real life pictures of an airplane flying faster than the sound it's creating, and you can actually see the cone wave in the airplane. So these are just still pictures, still photos of it. It's really kind of cool looking. When an airplane breaks the sound barrier, this is what it looks like. And I'm not going to play that whole video. I think you get the idea just from that little bit. So this is a great video of jets flying faster than the speed of sound. You'll see the cone wave. It's weird to have the jet flying at you and you don't hear it. And the reason we don't hear anything is because the jet is flying faster than the sound it's producing. All of the sound is behind it.
Watch the vapor build up on this airplane. Look at that. Oh, yeah!
So one more time with the explanation. The reason why there's no sound as it's approaching is because the airplane's flying faster than the sound it's creating. It's so cool.
Ladies and gentlemen, the Super Hornet high-speed pass.
So cool. So, there's some other examples that I have here in the notes. I'm not going to play all of them for you. You can find these videos relatively easily on YouTube if you want to.